So for the next 15 minutes, I'll give you some insight into the National Flying Laboratory Centre's research, but I'll also review some of the history of the National Flying Laboratory Centre and how it came about. So we'll start with looking at the foundations of NFLC, and then its evolution, and then where we are now with the flying lab. And then I'll also talk about some research that I've been involved with a number of colleagues over the last 10 years. Some of this research goes back to, including some EU research, some research that has been sponsored or supported by the ATI, the Aerospace Technology Institute. And then there's also some other work that I've been doing within Cranfield on application of CFD to flight testing. I'll then talk a bit about the future, and there'll be a summary, and then I think we'll go into questions following that. So if we go back 70 years, I've got a movie here to show you, which may spark some memories in some people. I'd actually encourage you, if you do appear in this movie, please put something in the chat, because it's quite an interesting 2 minutes. So I'll just play this now, and then we'll go into the rest of the lecture.
No matter what its type, an aircraft's place is the air, and a wind tunnel is the best place to study aerodynamics. Aerodynamics is the science which enables these students to assess the behavior of a plane in flight, and is an essential part of the 2-year course at the College of Aeronautics at Cranfield. Incidentally, this is no blackboard, it's the inspection window of a smoke tunnel. This student is studying vibration in a wind structure, and you'll see the same rig used again in a moment when they test the nose wheel of a comet. More important than the tests, however, is the reason why the students are here. The college was conceived in the stress of war, when shortage of trained aeronautical engineers left Britain in suspense. It must never do so again. Here is a supersonic wind tunnel which operates at speeds up to 3 times the speed of sound. As a result of the setting up of a vacuum, air can be passed at supersonic speeds over the hump in this test chamber, and by means of light projected onto mirrors, the effects can be studied visually on a screen. A case of seeing what you should hear. We're safe on this side of the observation window of the jet test house, but inside they need to take precautions. And that's because the shrill whine of a jet can be ear-shattering until it reaches a frequency which takes it beyond human hearing. For the study of rocket motors and ramjets, even greater protection would be needed, but at least we can show you for the first time the business end of a jet. So to the practical application of theory, and to more laboratory experiments in the air. Completely equipped for performance testing, the aircraft is just one more step in a far-sighted plan to ensure the ascendancy of British aeronautical technique. Each student has his own instrument panel in this plane, the flying laboratory of a modern university of the air.
So there you go. What a fantastic bit of footage for a couple of minutes. And of course, what is really exciting to see is at the end, the last 20, 30 seconds, which was really the foundations of NFLC. It dates back to the 1950s, that movie, but you need to go back even further than that, into the 40s, to see the foundation of the College of Aeronautics. I was very lucky enough to get hold of this brochure from 1947, and inside the brochure, what was really interesting, and I'd heard about the Department of Flight, was there was a section on the Department of Flight and all the other departments in the College of Aeronautics. And as the film alluded to, that it was a practical application in flight. And if you go into the brochure, and you look at the brochure, there's sections in the brochure on Department of Flight where it talks about what the objectives of the department were. And it was essentially to give real or actual flying experience and link the theories of flight to and flight test to actual other departments, aerodynamics, aircraft design. So there was a direct link with having the reality of flight to all of these other departments and to provide flight test knowledge to the students on the course. And this would be done with complete facilities, aircraft, and give that direct linkage. And also the objective of Department of Flight then was to instruct the latest methods in flight testing. So that the interesting thing with this, these statements is a lot of these statements are actually exactly what we're still doing now in the National Flying Laboratory Centre. So it's really reassuring to see that the foundations of where we were founded are still strong. At the time, the Department of Flight had 7 aircraft, including 3 Ansons and a Dove, and they also had Tiger Moss for light aircraft flying, which I'll talk a bit more about in a minute. As the Department of Flight evolved, the fleet from 7 aircraft clearly expanded. And if you look into the 60s, you can see there a picture just on the left-hand side of the fleet then, where they had a couple of Doves, they had some Osters, I think, a rotary wing, and jets. And so at this point, it's clearly expanded into doing different forms of testing. And if you look at the bottom there, there's a Lancaster, which is also in the top picture, which has been modified for laminar flow research on a swept wing. So even going back that far, there's a connection with research and with industry and working with industry to provide the students from the college the experience they needed before they would go into industry. If you look at the original brochure in 1947, there's some sections in the brochure for the Department of Flight which describe the syllabus. And the interesting thing there is if you look at some of the things that we're doing today with the Flying Lab, there's a lot of crossover, and a lot of things are fundamental to learning about flight test technique, connecting the flying laboratory activity to the other departments, which was in that original statement. That's still going on, and we're still doing things such as stability, basic aerodynamics, stalling. They're all things that we're promoting in the course now. The light aircraft flying, if you remember, the original Department of Flight had some Tiger Moss, I believe. This still goes on as well. This is a key part of the National Flying Laboratory Centre now, and it was the Department of Flight all those years ago. If you look in the brochure, the Department of Flight describes this activity as some of ab initio training to try and get students up to a solo level. And we don't do that entirely today, but we very much want to put the theory into practice with our students, and they have a chance to fly in our light aircraft when they come and do the courses at Cranfield, and giving them that feel of the aircraft and the feeling of flight allows them to link their theory to the practice, and that's always been part of NFLC. So as the Department of Flight evolved, eventually the fleet was modernized. As Dougie alluded, they got their first 3 Jetstreams in 1969 and were operating them from the early 1970s. There was a further Jetstream which was operated on behalf of Raycol, and you can see there that there's already a very strong connection with industry, particularly with the operation of someone else's aircraft to do research, industrial research. We kindly, Jack Stockford and Andy Foster and myself, we kindly had an interview with Dodge Bailey, one of the old heads of NFLC, and Dodge will appear again in a minute. And Dodge went through quite a lot of his flying period with NFLC. And what really surprised us was the vast range of industrial flight trials that were being carried out by NFLC as it evolved and connected with industry. And you can just see down there on the left bottom how many different companies were involved and using either their aircraft or NFLC aircraft, which were modified. There's still connections now. Meggitt is only last year was doing flight trials in the Jetstream. We had a very strong connection with BAE Systems, and that's linked to a Jetstream which they acquired. I'll talk a little bit more about that in a minute. So if we go into further evolution from the Department of Flight, the actual National Flying Laboratory Centre came about from a HEFKI proposal, which was put together by Martin Ashleby in the early 90s. It received significant support from very high up in the university, from Professor Ron Fletcher, who was Deputy VC at the time. And this allowed some subsequent HEFKI funding to come into the mix, which also allowed the NFLC to actually expand its activity with more university partners. And this is a key part of our activity now. So from starting to be reasonably Cranfield centric, the involvement of HEFKI meant that we could expand our activity and support many other institutions around the UK. And we're still doing that today. And we also support a university in Ireland, University of Limerick. And the research with industry continued with the Jetstream Mark Is, which were retired in around 2005 and replaced by this Jetstream Lima Alpha, which we're still operating today, although we're expecting to retire that in the middle of next year. I mentioned earlier about the close connection at some point was built up with BAE Systems. This in the last 15, even 20 years became a key activity with NFLC, in part because they had acquired a Jetstream Whiskey, which was extensively modified, and it was used in a number of flight trials. The relationship developed further, and eventually NFLC had that Jetstream on its air operator certificate, and some of the pilots from NFLC used to fly Whiskey with BAE Systems pilots. There was a significant flight trial which Whiskey and LA was the Lima Alpha was involved in, called Australia, to develop see and avoid technology for unmanned aerial vehicles. And there was a major flight done with Whiskey in controlled airspace in the last 5 or 6 years, I think, where there was a ground station operating an autopilot in Whiskey through a SATCOM link. And the controller on the ground station could also speak to controlled airspace, and that was done in UK controlled airspace up in Scotland. So it was a significant body of work which used that Jetstream, and it was a privilege for NFLC to be involved in that with BAE Systems. Whiskey is going to be retired, and we're looking at using it at Cranfield. It will stay at Cranfield, potentially to help teaching students. Now, test pilots are really a key part of National Flying Laboratory Centre, and this dates back all the way to the foundations of Department of Flight. If you look through the significant pilots in NFLC or Department of Flight, a test pilot was always a key part of that, going back from in the 40s and 50s to Group Captain Hockey, all the way through to Angus McVitie, who then Dodge Bailey took over from Angus McVitie, and Dodge Bailey was my first boss in NFLC, and our current test pilot, Simon Davies. So it's always been a core part of NFLC and will continue to be. Now, the picture in the top left, Chris Daggett was a very key member of NFLC for a long period of time, from what I understand, and he is standing no less next to Neil Armstrong, and apparently Neil Armstrong was in Cranfield and was involved at some point on a short course there, and he did visit Cranfield for other things. Chris is talking to him, and apparently Dodge told us that these were the days where you could invite someone to the front, and apparently Neil Armstrong came and sat in the front with Dodge, and Dodge said, "Would you like to land it?" And of course, Neil Armstrong, test pilot, grand pilot he was, landed a Jetstream, and apparently Dodge said, "Never seen such a good landing." So, and it's not easy to land a Jetstream nicely, so that tells you the pedigree of Neil, which we had the privilege to host. So moving forward, really, if we're in the present, NFLC is operating 3 aircraft currently. The Jetstream 31, which Lima Alpha, which will be retired next year. We're operating a Slingsby and a Bulldog. The Jetstream, we're now up to over 1,600 students a year from over 20 universities. We're flying in these flight test courses or flight test training courses. It was originally fitted out as a bespoke flying lab, and it's done very good service to the university, but it is now due to be replaced. The university is replacing it with the Saab that you can see at the bottom left corner. And this will be coming into service at some point in 2021. And in terms of flying students in probably mid-2021. The Slingsby continues to fly the students on flight experience, and the Bulldog, which we have, has gone under extensive modification the last 10 or 15 years, so that we can use it both for flying experience and for student, for research projects. Now, a key part of NFLC is how we operate our people. And we do have a large range of people involved in the operation, and we're under what's known as a Part SBO operation in terms of the regulatory framework. It's a great group of people. It's working really well, and at this point I do really need to say thank you to everyone in this group. We're not doing an easy thing, and we do it really well. We smile, we enjoy it all, and I have to really thank you for all of your efforts and your dedication. Now back to the Saab, which has been a key development in NFLC in the last 2 years. It's a significant project. It's a £3 million project, which is supported by Cranfield, by our university partners, by industry. Supported by alumni, and it really is going to transform our operation in the next year. So we have the aircraft. It's in Saab at the moment, with the modification process underway. There is going to be some new features in the aircraft, including a Wi-Fi cabin with more interactive experiments. We're measuring all of the key parameters which we used to measure, but we're updating also our systems in terms of we've got an updated inertial, and we should be able to do differential GPS, more cameras, more mounts. There's also a significant company that's going to be putting SATCOM into the aircraft for industrial work, and that will be related to the Digital Aviation Research and Technology Centre. So it will be a key part of that activity. And we will get to a position where there'll be a flight trials rack in the aircraft as well, which will allow us to again engage in industry, which is a key part of the NFLC activity. During the modification, we've had a number of key partners with the whole project as it's been going along. The design work's being done by Cranfield Aerospace Solutions, and Saab is in charge of the installation in Sweden at the moment. There's another company, Cytec in Derby, who have put a lot of effort into the interface and the software for the tablets, which will be going in the aircraft. And there's just an example here. We had an acceptance test last week where we went through some of the software, and it's looking really good. It's really easy to use interface. it's really it's right up there, all the latest technology and software which has been developed by Cytec. So thank you greatly for that. If we come back to the Bulldog, since I've been in NFLC, over a number of projects, it was modified in a EU Framework 7 project, and it involved putting fibre optic systems on the aircraft, which I'll talk a bit more about in a minute. We've done some further modifications in the last 2 years, and we've now got an air data boom, and we can measure position of the control surfaces, and we've got an ADC, an air data computer. So this aircraft is a sort of project, a continuing project development, and again, it's a very capable small airframe. Any industry partners that are interested in it, please contact me. I'll be delighted to show you around the aircraft. If we go back to the fibre optic sensor technology, there was a major EU project where this technology went on the aircraft, and it involved essentially putting some fibre optic pressure sensors on the aircraft, and also some strain sensors on the wing. And we did some flight trials with this equipment. Now, the actual, I'm proud to say that the fibre optics were all the fibre optics were fabricated at Cranfield in the engineering photonics laboratory and department that's run by Professor Ralph Tatum. And I continue to work very closely with Ralph. I've known Ralph for, since my PhD days, actually. And he runs a fantastic department. Ralph, you're an outstanding academic. You're a good colleague and friend as well. We've done a lot of work in this area on fibre optics and tried to apply them to aircraft, and it's been a really exciting area that I've been working with. Another area with Ralph on fibre optics that I've been working on is the BladeSense project, which was an ATI, aerospace technology project, which involved putting fibre optic technology in terms of shape and strain on a helicopter rotor. If you can look in the bottom corner here, you can see the bottom right corner, you can see the fibres and shape sensing fibres being fitted to the blade. There was then an interface on top of the rotor which transmitted all the data by Wi-Fi to a van, and this was done at Oxford Airport last year. And the helicopter didn't fly; it was tethered. The reason it didn't fly was the certification was outside the scope of a project. So we demonstrated the whole systems with a tethered situation with the helicopter. We had extremely good results. The rotating hub worked really well, and this will be the subject of some publications in the next year. But really successful application of fibre optic methods. Another fibre optic project which I was involved in with Ralph was putting the sensor, essentially the same sensor suite that was on the Bulldog aircraft, strain and pressure, into a transonic wind tunnel at ARA, and we demonstrated this technology up to Mach 0.82. We looked at unsteady pressure. If you look in the bottom left corner as well, the unsteady pressure sensors also gave us very good performance, really, compared to the datum Q-light sensors, and we got wing strain as well. And overall, it was a successful project, particularly given the environment that the fibers are in. Fibre optic sensors, they do present challenges. A lot of the challenges are related to the correction. You're generally measuring two measurand at once, so you might be measuring strain and temperature. And a lot of the work goes into the corrections that you have to do to get the performance you want from the instrument. But all of this work is ongoing and is an exciting area to work in. There's another slightly different project here, which is related to human factors in aircraft. And this was a project that was done with TNO and TU Delft. And what we were interested in was a misinterpretation of the artificial horizon. And you can see here, and there's a particular condition that you can get as a human called the leans, where your ears think you're you're leaning in one direction, but you're actually not. So you can be tricked. The ears can be tricked into thinking that you're not seeing what's actually happening. So we set up an experiment with Delft and TNO, where there was a very carefully designed set of flights that were flown by our test pilot Simon Davis, and we flew these flights on 50 Cranfield students, non-pilots, to see if we could get the leans effect and the misinterpretation. So here I'm just going to play a short movie. This is one of the flights that Simon Davis did. So what Simon will do is he'll bank the aircraft to the left very gradually with a blindfold on the student, and this will this will be slow enough, the bank will be slow enough so the ears don't pick it up. He'll then do a rapid acceleration to the right, which the student will detect, and then he'll hand control. And what we're looking for is if the student looks at the artificial horizon and the ear, the signal from the ear is stronger than his visual signal he gets from the effectively looking at the horizon, he'll bank back into the turn. So you'll see this. So I'll just play that now.
Okay, blindfold on, please. Blindfold on.
Here's a rapid roll back now coming up.
Okay, take the controls. 3, 2, 1, now.
And the student banks back into the
Excellent.
into the curve. So that was in terms of a result. That was the student had been disorientated because they banked back into the turn. So we published this data, and it gave some pretty conclusive evidence of the leans. We were getting the leans in our subjects. So the next bit of the presentation relates to some work I did on the Slingsby with there's an Erasmus student at Anna Neves, who was an excellent student. She's now a PhD student at Cranfield. This work was also done with Simon Davies, our test pilot, and an old colleague and friend, Badur Kanel, who works at Coventry University. Badur is a numerical methods expert in detached eddy simulation. The background here is stall spin. Now stall spin is still a significant issue in aviation and in general aviation in small aircraft. Any aircraft potentially can stall or spin, and typically the most prevalent areas of flight where you get stall and spin are in takeoff and climb. And the accident rate is still there, and it's still up to 30% of general aviation accidents that originate from stall and spin. So I'll talk a little bit about what stall and spin are, and then and how we can relate some research to that. So if we're looking at stall, stall is related to what's a key parameter in aircraft called angle of attack. Angle of attack alpha, and it's in condition where the boundary layer over the body or the wing or both will separate, which means it leaves the body, becomes turbulent in terms of a flow, and alpha, which is defined by a reference line on the aircraft and the flight path. You need a specific alpha to start to get separation and ultimately stall, and then loss of lift. So if you were plotting, for example, the lift generation from the body or the wing, as you increase alpha, the lift does increase, but you get to a point where the flow does separate, it becomes turbulent and separates off the back of the body, and you get unsteady flow, and you get an unsteady phenomenon called buffet, which vibrates the structure. The other significant thing with stall is that the drag rises significantly as well once you reach the stall point. If you push the stall further, then there's a chance that the aircraft can spin. So the best thing to do about spin is to run a couple of videos and show you what's involved in spin. So this first one is just sourced from NASA.
Repeatedly, Patton noses the aircraft skyward till the small plane stalls. It then pitches over and the spins begin.
2, 3, 4. Seems to be staying fairly steep. 5, 6. Stable. 7. Recovering, and it's responding slowly.
So clearly it's a very dynamic maneuver. If you're taking a pilot's point of view in the cockpit, this is a movie of a spin in the Slingsby with a colleague of mine, Rob Harrison. So I would hope it's reasonably clear to you that it's an unsteady condition, but actually it results from an asymmetric wing stall ultimately when you get into a stable spin condition. It's stable because eventually the rate of rotation settles down to a steady rate, and you can see that the aircraft descends almost vertically and rapidly. The actual center of gravity of the aircraft, it follows a helical path, and during that descent the aircraft is pitching, rolling and yawing, and the recovery, if it's possible, is you use the rudder and the elevator. Clearly the aeroplane we were flying is an aerobatic aircraft. It's certified to be spun and recovered, but it just illustrates the kind of, if you're not aware what to do as a pilot, potentially the confusing situation. And this is one of the reasons that there are fatalities when you have stall spin. If you go into the background of modeling, actually modeling stall and spin, there's a lot of data you need to get a good dynamic model. And there's a lot of coefficients, and typically these coefficients come from a number of different sources. But you can see here, there's a relationship between the angle of attack and some of these coefficients, which are lift, pitching moment, drag. They're complex relationships, and typically you get these relationships from rotary wind tunnel tests and spin wind tunnel tests. There's a number of different ways you can get them, but you do rely substantially on experimental methods to get these coefficients. There's issues with this, with scaling and other things, but there's been a lot of work done, for example, by NASA and other places in the UK that have done this in the past and looked at these phenomena and got the coefficients. There's actually a strong connection with Cranfield as well. There's an ex-Cranfield staff member who worked at the College of Aeronautics, Colin Martin, who's worked with NASA on this as well. But you can clearly see it's a complex situation in terms of data requirement to do some kind of model. And this is where I'm just tonight, for the remaining bit of my research, I'm going to present to you some computational methods that offer a complementary method to getting some of this type of data. And it would ultimately help aircraft design and the prediction of stall or spin. So to do this, we did a two-part experiment. We did an experiment in this Slingsby aircraft. We did an experimental in-flight part to the study, and we did a numerical study with computational fluid dynamics, and we compared the two from pre-stall to post-stall in terms of the predictions. The aircraft itself, it's an aerobatic aircraft, the Slingsby. It's got a very good G envelope. It's got also a good Reynolds number in terms of getting some predictions, and we can match that in the numerical model. So to actually go through, we start with basic straight and level flight data to get our lift and alpha relationship. We then use that to develop a steady computational fluid dynamics model. We then go back to the flight envelope, and we get Buffet data and alpha data in the stall. And then we look at our unsteady CFD solution and we compare them with experiment. Now, the actual straight and level flight tests are reasonably easy to manage. you do some simple equating of the airspeed, the engine power to get you a thrust, and you equate the thrust to the drag, and then you equate the aircraft weight to the lift. And by doing this on a simple straight flight path, where the flight path is straight and level, alpha is reasonably easy to measure, it's a steady kind of situation. So that's reasonably straightforward to get some data for your CFD validation. The challenge comes in the stall flight. In stall flight, the aircraft is now descending, and alpha is changing in the descent. So you have to somehow measure constantly alpha in the stall. There are methods such as booms that can be calibrated and used. In this case, I was looking at taking alpha measurements with some alternative methods. We didn't have the luxury of a boom on the Slingsby for this. And to get alpha in the stall, when the aircraft's descending, you have to measure flight path angle, and you have to measure effectively the pitch attitude simultaneously. And when you sum the two up, you get your measurement of alpha during the stall. The only major issue with this is however you measure your flight path angle, which you could use a ground speed and your descent speed. If you're doing this in a flight, you need to fly crosswind, because you're relying, for example, on your ground speed and your descent speed to get this angle, and therefore the atmosphere is moving, there's wind, you have to fly crosswind to get a more reliable estimation of lambda in using these simple methods. To get these two estimates of alpha in the stall, what method one we used was, again, and this, we didn't have a boom to validate these, but I was just to illustrate the sort of things you can do, is during the stall, we took data from with a camera mounted in the cockpit of a level, and then we monitored with another camera, the altimeter, and then we got our ground speed from a simple iPad. With method two, we had a autopilot drone called a Pixhawk, and the Pixhawk has a number of inertial accelerometers inside it. You can measure all your rates, and it also simultaneously measures your GPS, so you can get your ground speed like the iPad, but better at 5 Hertz, not 1 Hertz, but 5 Hertz. So using the pitch attitude from the unit and the GPS data, because the GPS data gives you altitude, you can get your flight path angle, and from the pitch attitude, you'd sum the two and you get your alpha in the stall. So we ran these two methods, and the method one, it gave us some estimates of the kind of angles, alphas we were getting. And because you have a simultaneous camera in the cockpit, you can see how it develops the stall develops into the buffet, and what kind of alphas you're expecting and what you think you're getting. And then the Pixhawk is the other two data sets here, where you see the flight path angle that's been estimated and alpha. And again, by noting the phenomena as you do the measurement, you can work out what alpha range you're going to get in a heavy stall. And here we were between 20 and 30 was heavy buffet and wing drop. Between 15 and 20 was initial stall. And the two were validating enough in terms of their range. Just a thing to note about the flying crosswind: if you don't fly crosswind, you can get some significant errors there, which I've just illustrated, depending on how well you can fly crosswind. You know how to fly crosswind because you get the Met data from the Met office before you do the flight, and then you do reciprocal headings and repeat data. The CFD model, this was developed using a CFD method called detached eddy simulation. We set up, Anna Neves drove a lot of this. We set up a half model with three mesh densities and with a wake region specifically set up for the stall and the wake from the stall. And then we had a number of measuring points to see what the performance of the model was like. And we ran the model initially for the steady state. We got reasonable validation. and then we went into the unsteady model, and these are typically kind of results that you get from the unsteady model. So just to point out main features here, you can see that there's a von Karman type shedding mechanism, which is developing from a trailing edge and shedding off towards the tailplane. There is actually an indication of significant tailplane interaction with the wake, and this was a finding for us, which we weren't aware of until we ran this model. And then you can see, if you look at the other view, the wing is substantially stalled, which is what we'd expect, but the tailplane isn't. So that's a good feature to have on your aircraft. So by running these simulations, it gives you some insight to whether you need to do some further testing, or to validate it, we decided to do further testing, and we also looked at the tailplane interaction. So as part of the validation, we did a further flight test where we put some accelerometers on the coaming. We had a camera in the cockpit again, monitoring pitch attitude through the instruments and the other instruments in the cockpit. And we used updated or uprated IMUs, inertial measurement or accelerometers, as we did the test, so they could measure up to 1 kilohertz. We also did a ground test before these flights to look at the natural frequency of the wing, because the validation was to look at the buffet and the stall, to look at the excitation of the structure, or what the accelerometers would pick up, and compare that to the CFD shedding frequency in that wake that I just showed you. So we wanted to see some discrimination between the natural frequency of a wing and the shedding frequency of the wake to make this comparison valid. And so on the ground, we were finding a natural frequency of a wing of about 6 hertz. The CFD was indicating 9 hertz or upwards. So we were reasonably confident if we could measure the buffet in the stall, we could do some comparisons. And so the data from the IMUs, we managed to window up different parts of the data for different angles based on the video footage. And if you take those windows and run a spectra on the data, you see what the frequencies are that are dominating that buffet and shedding in the flight. And then you can compare it. So this is the flight data. You can compare that dominant frequency in the shedding from the stall and the buffet to the frequency in the CFD from that model I showed you. And we got some pretty good matches. Depending on how you were measuring or predicting alpha, we were getting a few % match in terms of the frequency we were predicting from the CFD and what we were seeing in flight. So we were very happy with that. We consider that a good result, and we have published this work now. One of the outcomes from this test was that we saw in the CFD an interaction with the tailplane. So we went forward and did further tests, and we did a flight looking at the rear of the aircraft to see if there was any indication of this interaction, the wake interaction. This involved another ground test to look at the natural frequency of the tailplane. This time, the key frequency in the tailplane we found was around about 9 hertz, a natural frequency. If you remember from the previous slide, we were getting shedding frequencies of 9 to 11 hertz. So this looked quite close. And so we went flying to see what we could find. So Simon Davis went flying and he set the camera up. And this is the view we got looking at the tailplane now in the stall. So you can see now an interaction. So you could see there the interaction. There was clearly a significant interaction if you looked in that window on the tailplane. And eventually there was a progressive stall to the wing drop, and Simon recovered the aircraft. By the way, if you want to look at these videos, when we issue a PDF of this presentation, I've got some links and you can look at these videos in slow time if you want. So we took this data, this visual data from the camera, and we did some image processing on it. So that window you can put into some software which correlates image sequences. I've got some software that I've developed myself and I've used for many years, and I adapted it for this particular application. So we put that image sequence into this software, and then if you take, which generates vector maps, you take a specific vector from that image field, you can get a trace of what the tailplane is doing. And this is effectively like tailplane position with time. Then you apply a spectral analysis again, and what we found is there was indeed a significant interaction. We were getting a 9 Hertz, one of the dominant frequencies was 9 Hertz. So the wake frequency was almost matching the tailplane natural frequency. And that was a significant finding. We're going to publish this work. So just to finish now, I'm wary of the time. I've outlined to you what we've been doing, and this is why I want to take NFLC in the future. There's going to be a significant involvement with the Digital Aviation Research and Technology Centre, and NFLC, we've got a platform coming on board now with the Saab that will support that, particularly now there's a SATCOM system going on it. The Saab 340 will allow us to do a dual role, which is dating all the days back to the Department of Flight, where we support industry and we do our teaching activity with the aircraft. I also have a personal ambition that I think we should run NFLC on sustainable aviation fuels, and I think even within Cranfield we have quite a lot of expertise to possibly be able to do this. Just to illustrate, this field is really developing fast on sustainable aviation fuels, and even in the press recently, there's a plant in Germany that's going in at Frankfurt, Main, which will be making the fuels through carbon dioxide in the atmosphere, and also taking hydrogen from electrolysis, combining CO2 from the atmosphere with hydrogen to make enough fuel, in this case from 10 megawatts to power an A350 for a year. So this field's developing really quickly, and I think Cranfield can be part of this. And I would like to establish or help to establish a sustainable aviation research centre as part of this mix. Our STEM outreach continues to promote the aerospace and the community and our activities. So just to summarise, I've outlined where NFLC originated from, the Department of Flight, and also over the last 5 years, 5 decades even. Someone's on, if you could put it on mute, please. There's someone who's not on mute. Okay, thank you. So NFLC has engaged with industry for the last 5 decades, and we've helped with complex flight trials. We'll continue to do that. There's also a major investment from Cranfield and our partners in the Saab, which is going to continue this. And then in terms of research, NFLC will continue to develop research, aerodynamic instrumentation, human factors research, which I've given you a taste of tonight. Fibre optic sensors development and application will continue with Ralph Tatum, and the numerical methods that I've outlined tonight, hopefully that will continue to develop to help aircraft design. I just want to thank as well a few people before I finish very quickly. I want to thank Handley Page Association for allowing me to do the lecture tonight, the CCAAA, the Royal AeroSoc, thank you very much for your support too. Industry is key to NFLC, and I have to thank your support with the new aircraft and in the future, and all the previous work we've done with you. We've got some fantastic university partners, and NFLC would like to thank you for that and supporting the new lab. The senior management team at Cranfield, we would not be where we were without your continued support, and really thank you very much for that. And for promoting us, media, the Cranfield media, and the alumni and all the Cranfield alumni, thank you very much for your interest as well in NFLC and for attending tonight. I'm sure there's quite a few of you listening now, and the alumni team to support that. On a personal note, I'd like to thank Dodge Bailey. I wouldn't be here without Dodge. Dodge allowed me to come into NFLC originally, and he's been a fantastic supporter ever since and continues to be. Graham Braithwaite as a personal friend and a supporter of everything I'm doing, and Cranfield and NFLC. And over the last few months, it's become really apparent what massive supporters Andy Foster and Jack Stockford are of NFLC, and they've done significant amount of help to make this happen tonight. So thank you, Andy and Jack. And that's really me finished. So it's over to John.